So there's this question that's been haunting physicists for over a century now, and it's not what you might expect. It's not about numbers or equations or anything too abstract. It's actually something a lot simpler, something you've probably wondered about without really thinking about it. And that question is this. If you're sitting in a moving vehicle and you drop something, where does it fall? Think about that for a moment. You're in a train, moving smoothly at a constant speed. The windows are closed. There's no turbulence, no sensation of motion at all because it's so smooth and steady. You release your phone from your hand. It falls straight down onto your lap. It doesn't slide backwards. It doesn't float away. It falls straight down, exactly the way it would if the train were parked in the station. Now, that seems obvious, doesn't it? Of course it falls straight down. But here's where it gets interesting. There's someone standing outside the train, on the platform, watching you through the window. From their perspective, you and your phone are both moving sideways at, let's say, 60 miles per hour. And yet your phone still falls straight down relative to you. The platform observer sees the phone moving in a parabolic arc, describing a curved path through space while it falls. But you, inside the train, see it falling straight down. Same event, same phone, same gravity, two different observers, two different descriptions of what the phone does. And this simple observation is where the entire story of relativity begins. Not with Einstein, actually, not yet. It begins with someone who lived centuries earlier, someone who looked at falling objects and cannons and ships and water poured from jugs, and saw something fundamental about the nature of motion itself. The beginning, a man with a telescope. Let's go back to the late 1500s and early 1600s. Italy. A man named Galileo Galilei, who you probably know as the telescope guy, the man who pointed a lens at the sky and saw moons circling Jupiter, something that shattered the old beliefs about the Earth being the center of everything. But before Galileo was famous for what he saw in the stars, he had already figured out something about motion that was just as revolutionary, maybe more so, because it was about something we all experience every single day. Galileo was trying to understand how things move. Not why they move, not yet, just how. And he thought about boats. Specifically, he imagined himself below deck on a ship that's sailing smoothly across calm water. The ship isn't accelerating, not turning, just moving forward at a constant speed. In this cabin, with no windows, no way to see outside, he drops a stone. It falls straight down. He tosses a ball to a companion. It travels in a normal arc, like it would on land. He pours water from a pitcher into a cup. It pours normally. Everything in that cabin behaves exactly as it would if the ship were sitting still in the harbor. Now, you might think that's just obvious physics. Of course, things fall the same way. But what Galileo realized was something subtle and profound. There is no experiment, no measurement, no observation he could make inside that sealed cabin that would tell him whether the ship was moving or standing still. Not if the motion was smooth and constant, not if there was no acceleration, no jolt, no change in velocity. This is what physicists call Galilean relativity, and it's the foundation of everything that comes next. The laws of physics inside that cabin are identical to the laws of physics on solid ground. Motion at a constant velocity is invisible. It's undetectable. It's physically meaningless unless you have something else to compare yourself to. You and the stone and the water inside the cabin might be moving at 10 knots across the Mediterranean, but as far as physics is concerned, you might as well be parked. The ship's motion doesn't change any of the physics happening inside. You experience this principle every single time you're on an airplane. You're sitting at 35,000 feet, moving at roughly 500 miles per hour relative to the ground below. The air is smooth, no turbulence. You could get up and walk to the bathroom. You could pour a drink. You could drop something and watch it fall straight into your hand. All of this behaves exactly as it would if you were standing in your living room. The motion is invisible to you. Your body can't feel it. The physics can't detect it. It's only when the plane accelerates during takeoff or hits turbulence or decelerates as it lands that you notice the motion, because then it's changing. This principle held for centuries. Isaac Newton built his entire system of mechanics on top of this idea. His laws of motion work the same whether you're standing still or moving at constant velocity. Force equals mass times acceleration. That equation gives the same answer in a moving train car or in a stationary laboratory. The principle is simple and elegant. Motion is relative. There is no special state of being truly at rest in the universe. Everything is just moving relative to everything else. That was comfortable. That made sense. That's how physicists understood the world for over 200 years. And then something came along that couldn't be explained by this comfortable picture. Something that moved at a very specific speed, and that speed turned out to be the same for everyone, no matter how they were moving. That something was light. The peculiar behavior of light. In the middle of the 1800s, something remarkable happened in Scotland. A physicist named James Clerk Maxwell was working on the nature of electricity and magnetism, trying to understand how these two seemingly separate forces might be connected. He wrote down a set of equations, 4 equations actually, to describe how electric and magnetic fields behave. And when he started working through the mathematics, something unexpected fell out of the calculations. His equations predicted the existence of waves, oscillating ripples in electric and magnetic fields that would travel through empty space. And when Maxwell calculated how fast these waves would move, the speed came out to a very specific number, about 186,000 miles per second. He recognized that number immediately. That was the speed of light. Maxwell had just realized that light itself was an electromagnetic wave. That electricity, magnetism, and light were all aspects of the same underlying phenomenon. It was one of the most beautiful unifications in the history of physics, something that revealed a deep connection between forces that had seemed completely separate. But it came with a puzzle, and this puzzle was uncomfortable in a way that would trouble physicists for decades. Maxwell's equation said that light travels at this speed. Just the speed, not the speed relative to the Earth, not the speed relative to the Sun, not the speed relative to whatever object is producing the light. Just the speed. 186,000 miles per second, full stop. No variations, no relative motion, just an absolute speed. But this made no sense in the framework of Galilean relativity. Think about it. If you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the platform sees that ball moving at 80 miles per hour. The speeds add. That's what we expect. That's what we see with everything in the everyday world. Speeds add together based on relative motion. So if you're flying on a spaceship moving at half the speed of light and you shine a flashlight forward, shouldn't the light beam be moving at 1.5 times the speed of light from the perspective of someone standing still? That's what Galilean relativity would predict. The speed should add. But Maxwell's equations were saying no, the speed of light is the speed of light, period. It's the same for everyone. This was deeply strange, and physicists in the late 1800s felt the tension. They knew something was off. There was a contradiction between what they understood about motion and what the mathematics of light was telling them. And the way most of them tried to resolve this contradiction was by inventing something that sounds almost quaint to us now, the luminiferous ether, the ghost in the machine. The reasoning went like this. Every wave they knew about traveled through some kind of medium. Sound waves need air. Ocean waves need water. Vibrations need solid material. If light is a wave, what's it waving through? There must be some invisible substance filling all of space, something that would carry light the way air carries sound. They called it the luminiferous ether. Luminiferous meaning light-bearing. And it was supposed to fill the entire universe, providing a fixed background against which all motion could be measured. If the ether exists, then Maxwell's equations made sense. Light travels at 186. 0.000 miles per second relative to the ether. That's the speed in the ether's reference frame. Just like sound travels at about 767 miles per hour relative to the air, and as the Earth moves through space, it's also moving through the ether. There should be an ether wind blowing past us, just like you feel a breeze when you're moving through still air. This ether wind should affect how fast light appears to move in different directions. Light traveling in the direction of the ether wind should appear slightly slower, because you're trying to move through something that's also moving. Light traveling perpendicular to the ether wind should appear to move differently too. And the differences would be tiny, because the Earth's orbital speed is only about 18 miles per second compared to light's 186,000 miles per second. But tiny differences can be measured if you build the right instruments, and this is where one of the most famous experiments in the history of science comes into play. An experiment that was designed to detect the ether wind. An experiment that would lead to one of the most important null results in all of science. They found nothing. The experiment that changed everything. Albert Michelson was an American physicist, born in what is now Poland, raised in mining towns in the American West during the Gold Rush era. He became obsessed with measuring the speed of light. Not approximately. Precisely. He built instruments, refined them, built them again. By the 1880s, he was the most skilled experimenter in the world at measuring light speed. He could measure things that were incredibly small and incredibly precise. He partnered with Edward Morley, a chemist at what's now Case Western Reserve University in Cleveland, Ohio. Together they designed an experiment to detect the Earth's motion through the ether. They built something called an interferometer. Here's how it worked, and it's actually quite elegant. You take a beam of light and you split it using a special mirror that reflects half the light and lets half pass through. Now you have two beams of light traveling at right angles to each other. Each beam travels down a long arm, hits a mirror at the end and bounces back. When the two beams recombine, they create an interference pattern, bright and dark fringes. The pattern is exquisitely sensitive to any difference in how long it took the two beams to make their round trips. The idea was simple. If the Earth is moving through the ether, then one arm of the interferometer would be aligned with that motion and the other would be perpendicular to it. The beam traveling along the direction of the ether wind would take slightly different time than the beam traveling across it. That time difference would create a shift in the interference pattern. They could calculate exactly how big the shift should be. They built the apparatus on a massive stone slab floating in a pool of mercury so they could rotate it smoothly without vibrations. They ran the experiment in 1887, and they found nothing, no shift, no difference. No matter which way they pointed the device, no matter what time of day, no matter what time of year, the speed of light was the same in every direction. The ether wind wasn't there, or if it was completely undetectable, which amounted to the same thing. They repeated the experiment with greater and greater precision over the following years. Same result, nothing. The speed of light appeared to be the same for everyone in every direction, regardless of how the observer was moving. This was baffling. This was supposed to be proof that the ether existed. Instead, it seemed like proof that something was fundamentally wrong with the whole picture. Physicists tried to explain it away while keeping the ether alive. Hendrik Lorentz in the Netherlands and George Fitzgerald in Ireland independently proposed that objects moving through the ether physically contract in the direction of their motion. They get shorter, and this contraction would be exactly the right amount to cancel out the expected time difference in the Michelson-Morley experiment. Lorentz worked out a whole set of transformation equations that described how lengths and times would change for objects moving through the ether. The equations worked mathematically, they made the right predictions, but it was a patch, an explanation that saved the ether by adding a new assumption. The ether was still supposed to be real, the contraction was just a side effect of moving through it. And then in 1905, a 26-year-old patent clerk in Bern, Switzerland, looked at this entire puzzle and saw something completely different. He saw something that no one else had been willing to see, or maybe no one else had been able to see. What if there was no ether? What if the speed of light really was the same for everyone, not because of some contraction effect, not because of some mysterious medium, but because that's just how the universe actually works? What if you took that bizarre, counterintuitive fact, and instead of trying to explain it away, you accepted it as a fundamental law of nature and followed it wherever it led? The patent clerk's insight, that young man, was Albert Einstein. And in 1905, evaluating other people's inventions during the day and thinking about physics in his spare time, he published a paper that would change everything. The title translated from German means On the Electrodynamics of Moving Bodies. It's one of the most important scientific papers ever written. And what's remarkable about it is that it doesn't start with complicated mathematics or obscure experimental results. It starts with two simple assumptions, two postulates that Einstein asks you to accept. And then he shows you what logically follows from those assumptions. The first postulate is simple. It's just Galileo's old principle, updated for the modern age. The laws of physics are the same in all reference frames that are moving at constant velocity. Not just mechanics, all of physics. Electromagnetism too, all of it. The laws work the same whether you're standing still or moving smoothly at constant velocity. No experiment can tell you which one you're really doing. There's no privileged frame of reference, no special state of absolute rest. The second postulate is the strange one. The speed of light in a vacuum is the same for all observers. Regardless of the motion of the light source or the observer, it doesn't matter if you're racing toward the light or running away from it. It doesn't matter if the source is moving. You will always measure the same speed, about 186-282 miles per second. And if you're lying there thinking, wait, that can't be right. How can the speed of light be the same whether I'm moving toward it or away from it? Then you're having exactly the right reaction, because that second postulate flatly contradicts everything your everyday experience tells you about how speeds work. If you're driving towards someone at 60 miles per hour and they throw a ball at you at 30 miles per hour, you see that ball coming at 90 miles per hour. That's how velocities add in normal life. But light doesn't play by those rules. Einstein said, fine, let's accept that. Let's see what happens if we take this seriously. What happens is that the assumptions about space and time, assumptions so fundamental and so ingrained that nobody had ever seriously questioned them, turn out to be wrong. And the first thing that collapses, the first casualty of taking Einstein's postulates seriously, is the idea that two events happening at the same time for you must also be happening at the same time for everyone else. It's the idea that simultaneity is universal. That now means the same thing everywhere in the universe. The end of universal now, Einstein showed with a thought experiment involving a train and lightning strikes that this isn't true. Let's walk through it together, because once you understand this, everything else starts to fall into place. Picture a railway platform on a clear day. You're standing right in the middle of the platform, just watching. Here comes a long train moving at a significant fraction of the speed of light. We're in Einstein's imagination now, so let's not worry about realistic speeds. The train is moving fast. Really fast. At the exact moment the middle of the train is lined up with you, at the moment when you're face to face with the midpoint of the train, two lightning bolts strike simultaneously. One hits the front of the train, one hits the back. You see both flashes at exactly the same instant. And you know they happened at the same time because you're standing equidistant from both strikes. The light from both had to travel the same distance to reach your eyes. Fair enough? Two simultaneous events, lightning at the front, lightning at the back, same moment. But now let's think about what a passenger sitting in the middle of the train sees. She's also equidistant from the front and back of the train. If the two strikes really happened at the same moment, if they're truly simultaneous, she should also see both flashes arrive at the same time, right? But she doesn't. Here's why. The train is moving forward. In the tiny sliver of time it takes for the light from both lightning strikes to travel inward toward her position, she has moved forward slightly. She's moved toward the front of the train and away from the back, so the light from the front strike has a slightly shorter distance to travel to reach her eyes. The light from the rear strike has a slightly longer distance. She sees the front flash first. She sees the rear flash second. Now, you might think, okay, that's just a trick of perception. The light just reached her at different times because she was moving. The strikes were still simultaneous. She just needs to correct for her motion to figure that out. And in the old Newtonian universe, that's exactly what you would say. You would say the events were simultaneous, and she just received the signals at different moments. But here's where Einstein's second postulate changes everything. The passenger on the train has every right to consider herself at rest. The first postulate says all constant velocity reference frames are equivalent. She can say perfectly legitimately that she's sitting still and it's the platform that's moving backward, and in her frame, light travels at the same speed in all directions. She's equidistant from both ends of the train. Light from both strikes travels toward her at exactly the same speed, and yet one flash arrives before the other. If the speed of light is constant, if it's the same for her as it is for you, then the only possible conclusion is that the two strikes did not happen at the same time. In her reference frame, the front strike happened first. The rear strike happened second. They were not simultaneous. But you, standing on the platform using the exact same constancy of the speed of light, conclude that they did happen at the same time. They were simultaneous in your frame. And here's the thing, neither of you is wrong. Neither of you made an error. Neither of you is seeing an illusion. You simply have different nows. Events that are simultaneous in your reference frame are not simultaneous in hers. Simultaneity is not absolute. It's relative. It depends on your state of motion. Take a breath with that one. Because it's genuinely strange. We are wired so deeply to believe that now is universal, that this moment right now is the same moment everywhere in the universe, that letting go of that belief feels almost disorienting. But Einstein's logic is airtight. If you accept that the laws of physics are the same in all inertial frames, and if you accept that the speed of light is constant for all observers, then simultaneity cannot be absolute. It's not a feature of the universe, it's a feature of your particular state of motion. When time itself stretches, and once simultaneity falls apart, something even more startling follows. If two observers can disagree about whether two events happened at the same time, then they can also disagree about how much time passed between events. And that means time itself is not universal. It depends on how you're moving. This is time dilation, and it's one of the most famous and most counterintuitive results in all of physics. Let's ease into it with a thought experiment. Imagine the simplest clock you can possibly conceive. It's just two mirrors facing each other, one above the other, with a single pulse of light bouncing back and forth between them. Every time the light makes one complete round trip, down to the bottom mirror and back up to the top, that's one tick, one complete oscillation of the clock. That's it. That's the whole mechanism. Light bouncing between two mirrors. Now imagine this light clock is sitting on that same train we were talking about, oriented vertically. One mirror on the floor, one on the ceiling. The passenger on the train watches the light pulse go straight up, bounce off the top mirror, come straight back down. Up and down, up and down. Nice regular ticks. Regular as a heartbeat. But what do you see from the platform? You see the train moving sideways. And that means the light pulse isn't just going straight up and down. It's also moving sideways along with the train. From your perspective, the light doesn't trace a straight vertical path, it traces a diagonal path. It goes up and to the right, bounces off the top mirror, then comes down and to the right. A zigzag. Here's the thing about a diagonal path. It's longer than a straight vertical path. The light has to cover more distance in each tick as seen from the platform. But the speed of light is the same for you as it is for the passenger. You both measure it at 282 miles per second. That's not negotiable. The light doesn't speed up to compensate for the longer path. It moves at the same speed but has to cover a greater distance. If it's covering greater distance at the same speed, it takes more time. Each tick of the moving clock, as observed from the platform, takes longer than each tick as observed on the train. The moving clock runs slow, not because it's broken, not because something is interfering with the mechanism, not because of some mechanical effect of motion on the mirrors. It runs slow because that's how the geometry of space-time works. Time literally passes more slowly for the moving observer as measured by the stationary one. And before you think this is just some peculiarity of light clocks, imagine this. Suppose the passenger also has a regular wristwatch and a heartbeat and a biological aging process. If her light clock is ticking slowly as seen from the platform, but her wristwatch is ticking at the normal rate, then her wristwatch and her light clock would disagree with each other. That disagreement would let her determine her absolute velocity. She could figure out whether she's really moving or really stationary. But Einstein's first postulate says you can't do that. There is no experiment you can perform inside your own reference frame that reveals your absolute motion. So everything must slow down together. Her wristwatch, her heartbeat, her thoughts, the chemical reactions in her cells, the decay of radioactive atoms in her luggage. Everything slows down by exactly the same factor. Time itself dilates. There's a mathematical factor that describes how much time stretches or compresses. It's called the Lorentz factor, usually written with the Greek letter gamma. It depends on your speed relative to the speed of light. At everyday speeds, driving a car, flying in a plane, the Lorentz factor is so close to 1 that the time dilation is unmeasurably tiny. Billionths of a second over a whole lifetime. But as you approach the speed of light, gamma grows dramatically. At 90% the speed of light, time for the moving observer passes at less than half the rate of time for a stationary observer. At 99%, the factor is about 7. At 99%, it's over 70. The closer you get to the speed of light, the more time stretches. And at the speed of light itself, gamma becomes infinite. Time stops altogether, which is one of the reasons nothing with mass can ever reach the speed of light. You'd need infinite energy to get there, and time would cease to pass for you entirely. Now, all of this sounds deeply abstract. It sounds like a beautiful mathematical game with no connection to the real world. But here's what's remarkable. Time dilation is not theoretical. It's not speculation. It has been measured directly with real clocks in real experiments. One of the most famous confirmations happened in 1971. Two physicists, Joseph Hafele and Richard Keating, took 4 cesium atomic clocks and put them on commercial airplanes. Regular commercial flights, flying eastbound and westbound around the world. They left matching clocks on the ground at the United States Naval Observatory in Washington, D.C. as a reference. When the flying clocks came back, they compared them to the reference clocks. And they disagreed by tiny amounts, nanoseconds. But the disagreements matched Einstein's predictions with remarkable precision. The eastbound clocks, which were moving faster relative to the Earth's center because they were flying in the direction of the Earth's rotation, lost time compared to the ground clocks. The westbound clocks, moving slower relative to the Earth's center, gained time. Exactly as relativity predicted, the effect was tiny, but it was measurable. And it was real. And if that feels too small to matter, consider this. The GPS satellites orbiting above your head right now are moving at about 700 miles per hour relative to the ground. That's fast by human standards, but it's a crawl compared to light. And yet the time dilation effect is real and significant enough that if the GPS system didn't account for relativistic corrections, your position would drift by about 10 kilometers per day. Your phone's map would be useless within an hour. Every time you use GPS to navigate to a restaurant or find your way home, you are relying on Einstein's relativity being correct. The engineers who designed the system had to bake these corrections into the satellite software. Relativity isn't philosophy, it's engineering, it's practical, it's real. The paradox of the twin. But time dilation opens a door to something even stranger. If a moving clock runs slow, and if all processes in a moving frame slow down together, then a person traveling at high speed genuinely ages more slowly than a person standing still. This isn't a metaphor, it's physical. A twin who flies to a distant star at 90% the speed of light and comes back will be younger than the twin who stayed home. Genuinely, biologically, measurably younger. Fewer heartbeats will have occurred in the traveling twin's body. Fewer cells will have divided. Less time will have passed for them in every meaningful sense. This is the famous twin paradox. And it has puzzled people since Einstein's day, because you might immediately think, wait, isn't motion relative? The traveling twin sees the Earth flying away. She watches Earth recede into the distance at a tremendous speed. Then she turns around and watches Earth approach. From her perspective, she's standing still, and the Earth is the thing that's moving. So why wouldn't she age more slowly than the stay-at-home twin? Why can't she say that the Earth is the one that's in motion and therefore the Earth-bound twin should be younger? The situation seems symmetric. So who's really younger when they meet up again? And the answer reveals something subtle and important about relativity. The situation is not symmetric. And the reason it's not symmetric is that the traveling twin has to turn around. She has to decelerate, reverse direction, and accelerate back. During that turnaround, she is not in an inertial frame. She's accelerating. She feels forces. She knows she's the one who changed direction. The stay-at-home twin floats along in the same inertial frame the entire time. There's no acceleration, there's no change. There's an asymmetry, and that asymmetry is what breaks the apparent paradox. When they reunite, the traveling twin is genuinely younger. The math works out cleanly, and the result has been confirmed with particle experiments. Muons created in the upper atmosphere by cosmic rays, for instance, live longer than they should precisely because they're moving so fast relative to us that their internal clocks are dilated. The moving muons age more slowly. They survive longer. Time dilation is real. Space contracts too. But time dilation is not the only consequence of Einstein's two postulates. Because if time can stretch, it turns out space can contract too. And the relationship between the stretching of time and the compression of space leads to something that would transform how we think about the universe itself. An object moving relative to you appears shorter along its direction of motion, not because it's being squeezed by some physical force, not because anything is pushing on it, but because of how the geometry of space-time works. The object in its own frame is exactly the same length it's always been. You haven't changed it, you haven't compressed it. But from your frame, watching it zip by, it's contracted. The amount of contraction is governed by the same Lorentz factor that governs time dilation. Here's how to think about it. Imagine a spaceship flying past you at 87% of the speed of light. At that speed, the Lorentz factor equals about 2. So if the spaceship is 100 meters long in its own rest frame, if the astronauts inside measured it nose to tail and got 100 meters, then you, standing on the ground watching it fly by, would measure it as only 50 meters long. Half the length. The spaceship is compressed along the direction it's traveling. The astronauts inside notice nothing unusual. Their ship feels the same to them. Their rulers haven't changed. They measure it and get 100 meters, just like always. But from your perspective, everything about that ship in the direction of motion has been squished by a factor of 2. And here's what's wild about this. It's completely reciprocal. From the astronaut's perspective, they're sitting still and you're the one flying past them at 87% the speed of light. So they would measure you and your planet and your rulers as being contracted by a factor of 2 in the direction of relative motion. Both of you are right. Both measurements are correct. There's no contradiction because you're measuring from different frames. And the act of measurement itself depends on what's simultaneous where. Remember that simultaneity is relative. Length measurement depends on marking both ends of an object at the same time. If your simultaneous now is different from my simultaneous now, we'll get different lengths. It all hangs together. It's consistent. This is different from what Lorentz and Fitzgerald had proposed back in the 1890s. For them, the contraction was a real physical squishing caused by motion through the ether. The ether was doing something to the object. For Einstein, there is no ether. The contraction isn't caused by anything acting on the object. It's a consequence of the structure of space-time itself. It's what measurement looks like when two observers are in relative motion, and the speed of light is the same for both of them. The math is the same. The formula is identical. But the physics underneath is profoundly different, and that difference matters enormously, because Einstein's version doesn't need the ether, doesn't need any mysterious medium, doesn't need any hidden mechanism. It flows naturally from his two postulates, and leads to the deeper understanding that came next, the geometry of the universe. So now we have time dilation and length contraction. Moving clocks run slow, moving rulers shrink. These aren't two separate phenomena that happen to coexist. They're two faces of the same underlying reality. They're projections of something deeper. And seeing that something deeper required the help of a mathematician named Hermann Minkowski. Minkowski was Einstein's old mathematics professor from his student days. And he had a profound realization. He saw that Einstein's special relativity wasn't really about time behaving strangely and space behaving strangely as separate things. It was about time and space being aspects of a single four-dimensional structure, space-time. Think about ordinary three-dimensional space: left, right, forward, backward, up, down. Three directions, three coordinates. If you want to specify where something is, you give three numbers: your latitude, your longitude, your altitude. Minkowski said, add a fourth coordinate: time. Every event, not just every place, but every event is a point in this four-dimensional spacetime, a point that has a where and a when. You can't fully describe anything that happens without specifying both. And here's the key insight. When you rotate an object in ordinary three-dimensional space, its shadow on the wall changes shape. Think about holding a pencil under a lamp. If you hold it straight up, the shadow is just a dot. Tilt it sideways and the shadow stretches into a line. The pencil itself hasn't changed. It's the same length no matter how you hold it. But the shadow, the projection onto a lower dimensional surface, changes depending on the angle. What Minkowski realized is that space and time individually are like those shadows. They're projections of the four-dimensional reality onto different slices. When two observers are in relative motion, they're essentially looking at different angles. One observer's slice of space at this moment is tilted relative to the others. And that tilt is what causes all the strange effects we've talked about. Time dilation, length contraction, the relativity of simultaneity. None of these are paradoxes or illusions. They're just what happens when you project a four-dimensional object onto different 3+1 splits. And just like the pencil has a real invariant length that doesn't change when you rotate it, space-time has an invariant quantity that doesn't change when you switch between frames. It's called the space-time interval. For any two events, you can compute this interval, and every observer in every inertial frame will agree on its value. The formula looks almost like the Pythagorean theorem, but with a crucial twist. In regular space, the distance between 2 points is the square root of x squared plus y squared plus z squared. In space-time, the interval involves time and space, but time enters with the opposite sign. It's the square root of c squared times delta t squared minus delta x squared minus delta y squared minus delta z squared. That minus sign is everything. It's what makes space-time fundamentally different from ordinary four-dimensional space. It's what gives space-time its peculiar geometry, what physicists call Minkowski geometry. The point is that the minus sign allows time to behave differently from space while still being woven together with it. This framework, Minkowski space-time, gives us something incredibly powerful. It gives us a way to visualize and reason about relativistic effects. Geometrically, you can draw space-time diagrams with time going up the vertical axis and space going along the horizontal axis. The history of any object becomes a line through this diagram. Its world line. A stationary object traces a vertical line just moving forward in time. A moving object traces a tilted line. Light always travels along lines tilted at exactly 45 degrees, and all of special relativity becomes geometry. Time dilation is the difference between the length of a world line and its projection onto someone else's time axis. Length contraction is the difference between the spatial extent of an object measured along different slices of simultaneity. The twin paradox becomes immediately visible. The traveling twin's world line is bent. It takes a shorter path through spacetime. And in Minkowski geometry, because of that crucial minus sign, shorter paths through spacetime correspond to less elapsed time. It's the opposite of what your spatial intuition would tell you. In ordinary space, a straight line is the shortest path. In spacetime, the straight line is actually the longest path in terms of proper time. The twin who stays home, who follows the straight world line, ages more. The twin who zigzags through spacetime ages less. It's all right there in the geometry. Einstein himself was initially skeptical of Minkowski's geometric reformulation. He reportedly called it unnecessary learnedness at first. But within a few years, Einstein would desperately need Minkowski's framework. It would turn out to be absolutely essential for the next great leap. The leap that took Einstein a full decade of struggle, wrong turns, and near breakdowns. The greatest intellectual effort. The leap from special relativity to general relativity. From equations that deal only with constant velocity motion to a theory that handles acceleration and gravity. Because here's what was nagging at Einstein almost immediately after 1905. Special relativity works beautifully. The math is elegant. The predictions are confirmed. But it has a limitation built right into its name. It's special. It applies only to inertial frames. Frames moving at constant velocity relative to each other. The moment you introduce acceleration, the moment you try to deal with forces that change your speed or direction, special relativity alone isn't enough. And the most obvious, most universal force that accelerates things is gravity. Every object in the universe with mass pulls on every other object. You're being pulled toward the center of the Earth right now. The moon is being pulled toward the Earth is being pulled toward the sun. Gravity is everywhere, and it accelerates everything. And special relativity has nothing to say about it. Newton's theory of gravity had reigned supreme for over 2 centuries. It described gravity as an instantaneous force acting across empty space. The sun pulls the Earth, and this pull acts immediately across 93 million miles with no delay. But Einstein had just shown that nothing, no signal, no influence, no information can travel faster than the speed of light. So, Newtonian gravity, with its instantaneous action at a distance, was fundamentally incompatible with special relativity. Something had to give. Einstein knew it. As early as 1907, just 2 years after his special relativity paper, he had what he later called the happiest thought of his life. And it started with a very simple question. A thought experiment. A person falling off a roof. The happiest thought. Imagine you're standing on top of a building. You step off the edge. This is just a thought experiment. Einstein's favorite tool. You step off and you begin to fall. Now, during that fall, before you hit the ground, what do you actually feel? And the answer, the crucial answer, is nothing. You feel weightless. If you had a ball in your hand and you let go of it during the fall, it wouldn't drop away from you. It would float right there beside you, falling at exactly the same rate. If you had a scale under your feet, it would read 0. For those few seconds of freefall, gravity has effectively vanished from your experience. You can't tell the difference between falling freely in a gravitational field and floating in deep space far from any massive object with no gravity at all. That realization was Einstein's happiest thought, not the falling part. The realization of what it meant. Because if a person in freefall can't distinguish their situation from zero gravity, then gravity isn't quite what Newton said it was. It's not just a force pulling on things. It's something deeper. Something more intimately connected to the nature of space and motion itself. Einstein formalized this insight into what he called the equivalence principle. And it's one of those ideas that sounds almost too simple at first but turns out to be extraordinarily powerful. Here's how it works. Imagine you're inside a closed room. No windows. No way to see outside. You feel your feet pressing against the floor. You feel weight. Normal weight. Normal gravity. Now there are two possible explanations for what you're experiencing. 1. The room is sitting on the surface of the Earth, and gravity is pulling you down. 2. The room is out in deep space, far from any planet or star, but it's accelerating upward. A rocket engine on the bottom is pushing the floor up into your feet at exactly 32 feet per second squared, or 8 meters per second squared if you prefer. Einstein's claim is that no experiment you can perform inside that room will tell you which situation you're in. Gravity pulling you down and acceleration pushing the floor up into you are, locally, in your immediate vicinity, completely indistinguishable. They're the same thing. Think about what that means. It means gravity and acceleration are deeply equivalent, not just similar, not just analogous, equivalent. And if they're equivalent, then anything you learn about acceleration applies to gravity too. This is the key that unlocks everything that follows. The long struggle. Einstein had this insight in 1907, and you might think the rest came quickly. It did not. The journey from the equivalence principle to the full theory of general relativity took 8 years, from 1907 to 1915, and it was by Einstein's own account the most intellectually grueling period of his life. He said that compared to general relativity, special relativity was child's play. And he wasn't exaggerating. Here's the problem. The equivalence principle tells you that gravity and acceleration are the same. But turning that insight into a complete mathematical theory of gravity, one that replaces Newton's theory, is consistent with special relativity, and makes testable predictions, that's a monumental task. Einstein needed entirely new mathematics. Mathematics he didn't yet know. He needed the tools of differential geometry, the study of curved spaces. This was advanced, pure mathematics, centuries ahead of what Einstein had learned in school. And in 1912, Einstein knew he needed help. So he reached out to an old friend, Marcel Grossmann, a mathematician he'd known since their student days at the Swiss Federal Polytechnic in Zurich. Grossmann had actually helped Einstein get his job at the patent office years earlier. He'd made a phone call to the right person. Now Einstein needed Grossmann again. And the story goes that Einstein showed up at his door and essentially said, "You have to help me, or I'll go crazy." And Grossmann, to his enormous credit, dove in. He introduced Einstein to the mathematical tools he needed. Tensor calculus, the Riemann curvature tensor, the metric tensor that describes the geometry of spacetime at every point. Together, they published a preliminary theory in 1913 called the Entwurf theory. Entwurf, meaning outline or draft in German. It was close, but it wasn't right. The equations had problems. They weren't fully generally covariant. That's a technical way of saying the equations changed their form depending on which coordinate system you used. Einstein wanted equations that looked the same no matter how you describe spacetime. That was the whole point. The laws of physics should be the same for all observers, not just inertial ones. But he couldn't quite get there. He convinced himself through a flawed argument that fully covariant equations were actually impossible, that you had to give up some of that mathematical freedom. And so he spent nearly 2 years, 1913 and 1914, working with equations he suspected were wrong but couldn't see past. The pressure was mounting. Other physicists were circling the same problem, and one in particular would push Einstein to the breaking point. His name was David Hilbert. He was arguably the greatest mathematician alive at the time, based in Göttingen, Germany. In the summer of 1915, Einstein gave a series of lectures at Göttingen, and Hilbert became fascinated by the problem of gravitational field equations. He started working on it himself, using his own formidable mathematical toolkit. And he was fast. Hilbert had spent decades mastering the kind of mathematics Einstein was still struggling with. Variational principles, Lagrangian methods, the deep algebraic structures of differential geometry. This was Hilbert's home turf. And now he was applying all of it to the same problem Einstein had been wrestling with for years. Picture this. It's autumn 1915, and Einstein is in Berlin, and Hilbert is in Göttingen. They're both racing toward the same finish line. They're exchanging letters, sometimes cordial, sometimes tense. Einstein is sharing some of his ideas, and Hilbert is sharing some of his. And both of them know that whoever gets the correct gravitational field equations first will have accomplished one of the greatest feats in the history of physics. And Einstein is terrified, not just because he might lose priority, though that matters to him, he's human, but because this has been his theory, his vision, his decade-long obsession, the idea that someone else might complete it, someone who picked it up almost casually over the summer. That's agonizing. November 1915. November 1915 is one of the most extraordinary months in the history of science. Einstein presented 4 papers to the Prussian Academy of Sciences, one each Thursday, November 4th, 11th, 18th, and 25th. And over those 4 weeks you can watch him in real time, correcting his course. Abandoning the Entwerf theory, circling closer and closer to the right answer. On November 4th, he presented a new set of field equations that were more general than the Entwerf equations, but still not quite right. On November 11th, he revised them again, and then on November 18th, he did something remarkable. He used his still incomplete equations to calculate the precession of Mercury's orbit, and the answer came out right. Mercury, the closest planet to the Sun, has an orbit that's slightly elliptical, and the long axis of that ellipse slowly rotates around the Sun over time. This is called the precession of the perihelion. Most of that precession is explained by the gravitational tugs of other planets, Jupiter, Venus, and so on. But after you account for all of those, there's a leftover amount, about 43 arcseconds, and Newtonian gravity simply cannot explain it. Astronomers had known about this discrepancy since the 1850s. Urbain Le Verrier, the same Le Verrier, who had brilliantly predicted the existence of Neptune by analyzing irregularities in Uranus's orbit, pointed out that Mercury's orbit didn't quite behave. People had proposed all sorts of explanations. Maybe there was another planet even closer to the Sun, a hypothetical world they called Vulcan. Astronomers searched for it for decades. Some even claimed to have seen it. But it wasn't there. And now here's Einstein in November 1915 with equations that aren't even in their final form yet, and he plugs in the numbers for Mercury's orbit, and out comes 43 arcseconds. Exactly. He later told a colleague that when he saw the result, his heart palpitated. He was so excited he couldn't work for days. Think about what that must have felt like. You spent 8 years building a theory that most of your colleagues think is too abstract, too mathematical, maybe even misguided. You've gone down wrong paths, you've published flawed equations, you've argued yourself into corners, and then the universe hands you this gift. A number that matches perfectly an anomaly that had puzzled astronomers for over 60 years. In that moment, Einstein knew he was on the right track. Not close. Not approximately. Right, but he still didn't have the final equations. That came 1 week later. On November 25, 1915, Einstein presented the complete generally covariant field equations of general relativity. These are the Einstein field equations. And they're often written in a beautifully compact form. The equation says that the Einstein tensor, which describes the curvature of spacetime, equals 8 pi times the gravitational constant divided by c to the 4th power times the stress-energy tensor, which describes the distribution of matter and energy. In words, matter tells spacetime how to curve, and curved spacetime tells matter how to move. That's the whole theory. That's the essence of it. In one line. Hilbert submitted a paper containing gravitational field equations to a journal on November 20, 1915, 5 days before Einstein's final presentation. So did Hilbert get there first? This has been debated for a century, and it's one of those historical puzzles that probably doesn't have a clean answer. What we do know is that the published version of Hilbert's paper, which came out in March 1916, includes the correct field equations. But there's evidence that Hilbert's original manuscript was revised in proof, and the revisions may have been significant. Most historians today give Einstein clear priority for the physical theory, the conceptual framework, the equivalence principle, the geometric interpretation of gravity. All of that was Einstein's from the beginning. Hilbert approached it as a mathematical problem and derived the equations using elegant variational methods. But Hilbert himself later acknowledged Einstein's priority. Einstein did the work, not the mathematicians. The physical geometry of reality. So by the end of November 1915, the theory of general relativity existed in its final form. But having the equations and understanding what they predict are two very different challenges. Einstein's field equations are extraordinarily difficult to solve. They're a set of 10 coupled nonlinear partial differential equations. Nonlinear means the solutions don't add up in simple ways. You can't just take two solutions and combine them. This makes them fiendishly hard to work with. Einstein himself could only solve them approximately using various simplifying assumptions. But within weeks, literally weeks, a German physicist and astronomer named Karl Schwarzschild found an exact solution. And the circumstances are almost unbelievable. Schwarzschild was serving in the German army on the Eastern Front during World War I. He was stationed in Russia, calculating artillery trajectories. And in whatever spare moments he could find, he was reading Einstein's papers and working through the mathematics of general relativity. In December 1915 and January 1916, while literally at war, he derived the first exact solution to Einstein's field equations. The solution describing the gravitational field outside a spherical non-rotating mass. He sent the results to Einstein, who presented them to the Prussian Academy in January 1916, reportedly delighted that such an elegant solution existed. The Schwarzschild solution is foundational. It describes how space-time curves around objects like stars and planets. And it's the basis for most of the predictions of general relativity. But it also contains something strange. Something Schwarzschild himself and Einstein and nearly everyone else at the time thought was just a mathematical curiosity, not something physical. At a particular distance from the center of the mass, a distance that depends on how much mass there is, the mathematics of the solution does something peculiar. The equations develop what looks like a singularity, a point where certain quantities blow up to infinity. For an object like the Sun, this critical distance, now called the Schwarzschild radius, is about 3 kilometers. Since the Sun's actual radius is nearly 700,000 kilometers, the Schwarzschild radius is buried deep inside, and the solution only applies outside the mass. So it doesn't matter in practice. But the question lingered. What if you had an object so dense, so compressed, that its physical size was smaller than its Schwarzschild radius? What would happen then? The road to black holes. That question would take decades to answer, and the answer would turn out to be one of the strangest predictions in all of physics. But the theory needed to be tested first. Einstein had made specific quantitative predictions. The bending of starlight passing near the sun, the gravitational red shift of light, the precession of Mercury, and the scientific world wanted proof. Mercury's precession was already known and already matched, which was powerful but retrospective. The gravitational red shift was incredibly difficult to measure with the technology of the time. So the spotlight fell on one prediction that could be tested dramatically and publicly: the bending of light by the sun. And this is where one of the great stories of 20th century science begins. A story involving a total solar eclipse, a British astronomer with a conscience, and a result that would make Einstein the most famous scientist on Earth overnight. The astronomer's name was Arthur Stanley Eddington. He was based at Cambridge. Eddington was one of the few people outside of Germany and the Netherlands who understood general relativity in its early years. Partly because he was brilliant. Partly because a Dutch physicist named Willem de Sitter had sent him copies of Einstein's papers during the war, when scientific communication between Britain and Germany had essentially stopped. Eddington received these papers and worked through the mathematics himself. He became one of general relativity's earliest and most passionate advocates in the English-speaking world. And that combination, his deep understanding of the theory, his position at one of Britain's most prestigious institutions, and something else, something more personal, would place him at the center of the most famous scientific test of the 20th century. Eddington was a Quaker, a devout one, and as a Quaker he was a conscientious objector to the war. This was 1917-1918, the bloodiest years of the First World War. And in Britain, conscientious objectors were not treated kindly. Eddington was of military age, and the authorities wanted him to serve. His colleagues at Cambridge, particularly the astronomer Frank Dyson, who was the Astronomer Royal, intervened on his behalf. They argued that Eddington was far too valuable to science to be sent to the trenches. But the exemption board wasn't entirely convinced. They granted him a deferment with a condition: he had to be engaged in important scientific work. And Dyson, who was already aware that a total solar eclipse was coming in May 1919, saw an opportunity. He argued that testing Einstein's prediction of light bending was precisely the kind of important scientific work that justified Eddington's exemption. So in a very real sense, the most famous experiment in the history of general relativity was partly arranged to keep a pacifist astronomer out of prison. Think about that for a second. The war shaped everything. It shaped who had access to Einstein's papers. It shaped who was in a position to test them. It shaped the motivation for organizing the expedition in the first place. Science doesn't happen in a vacuum. It happens in the middle of messy, complicated human lives. The eclipse expedition, the eclipse itself, May 29, 1919. A total solar eclipse would be visible along a narrow band crossing the Atlantic. And two expeditions were organized. One, led by Eddington himself, went to the island of Principe, off the west coast of Africa. The other, led by Andrew Crommelin and Charles Davidson, went to Sobral in northern Brazil. The idea was straightforward in concept, even if it was incredibly difficult in practice. During a total solar eclipse, the moon blocks the sun's light, and for a few precious minutes you can see stars that are very close to the sun in the sky. Stars whose light has passed right by the sun on its way to Earth. If general relativity was correct, the sun's gravity would bend that starlight slightly, making those stars appear to be in positions slightly different from where they actually are. The predicted deflection was tiny, about 1.75 arcseconds for a star right at the edge of the sun. An arcsecond is 1/3600th of a degree. So you're looking for an incredibly small shift in apparent position. And here's what made this test so decisive. Newton's theory of gravity also predicted light bending, but only half as much. About 0.87 arcseconds. This was actually something Einstein himself had calculated first back in 1911, before he had finished general relativity. When he was using an incomplete version of the theory, his prediction matched the Newtonian value. But by 1915, with the full theory in hand, the prediction had doubled. The factor of 2 came from the curvature of space itself, not just the effect of gravity on the energy of light, but the additional effect of curved spatial geometry on the path. So the eclipse test wasn't just about whether light bends near the sun. It was about whether it bends by the Newtonian amount or the Einsteinian amount. A factor of 2. A clean, testable difference. The expedition set out in March 1919, months before the eclipse. Because getting to these remote locations took time. Eddington arrived at Principe and set up his equipment. Telescopes, photographic plates, clockwork drives to track the stars during the eclipse. And then on the morning of May 29th, it rained. Heavy tropical rain, clouds everywhere. Eddington later wrote about the anxiety of that morning. Watching the sky, waiting. The rain stopped before totality, but clouds lingered. He managed to take 16 photographic plates during the eclipse, but most were useless because of the cloud cover. Only a couple showed star images clear enough to measure. The Sobral team had better weather. Mostly, though they had their own problems. One of their telescope mirrors had been distorted by the tropical heat, so an entire set of plates from one instrument had to be treated with caution. But their other instrument, a smaller 4-inch telescope, produced good results. Analyzing the plates took months. You couldn't just glance at them and see the deflection. You had to carefully measure the positions of stars on the eclipse plates and compare them to reference plates of the same star field taken months earlier when the sun was nowhere near those stars. The comparison required meticulous work, accounting for the scale of the plates, the optical properties of the telescopes, atmospheric effects, a dozen other sources of error. By September, Eddington had his results, and on November 6, 1919, a joint meeting of the Royal Society and the Royal Astronomical Society was convened in London. The room was packed. The portrait of Isaac Newton looked down from the wall, and this detail almost feels too perfect to be true, but it is. J.J. Thomson, the president of the Royal Society and the discoverer of the electron, presided. Dyson presented the results. The Sobral plates from the Good telescope gave a deflection of about 1.98 arcseconds. Eddington's Principe plates gave about 1.61 arcseconds. The average was close to Einstein's predicted 1.75. The Newtonian prediction of 0.87 was clearly ruled out. Thomson declared it one of the greatest achievements of human thought. The next morning, the Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." And within days, Albert Einstein went from being a well-known physicist in academic circles to being the most famous scientist in the world. A genuine global celebrity. It happened almost overnight, and it never really faded for the rest of his life. The remarkable decades. But here's something worth being honest about. The 1919 results were not as clean as the story sometimes suggests. The error bars were large. The Principe data was based on very few usable stars. The discarded Sobral plates from the heat-warp telescope actually gave a value closer to the Newtonian prediction. Some critics later argued that Eddington had been too hasty in dismissing that data. There's been a long historical debate about whether Eddington's prior belief in Einstein's theory influenced his analysis, whether he was seeing what he wanted to see. The consensus among modern historians of science is that Eddington's results were legitimate, but marginal. He got the right answer, but with less certainty than was claimed at the time. The truly definitive confirmations of gravitational light bending came later with better technology. Radio interferometry in the 1960s and 1970s measured the deflection of radio waves from quasars passing near the Sun with far greater precision, and they confirmed Einstein's prediction to within 1%. So Eddington was right. But he was also a bit lucky, and the public sensation that followed was disproportionate to the actual strength of the evidence in 1919. But that's how science and media interact then as now. What the 1919 eclipse really did was change the cultural status of the theory. Before the eclipse, general relativity was a mathematical tour de force that most physicists hadn't even read, let alone understood. After the eclipse, it was front-page news around the world. Einstein became a symbol of genius, of abstract thought, of the power of pure theory to reveal hidden truths about the universe. And yet, for decades after that, general relativity occupied a strange position in physics. It was admired, respected, considered almost certainly correct, but it was also somewhat sidelined. Through the 1920s, 1930s, 1940s, and into the 1950s, the real action in physics was in quantum mechanics and nuclear physics. That's where the exciting discoveries were happening. That's where the funding went. that's where the brightest young minds were drawn. General relativity was seen as a beautiful but somewhat sterile theory. It made predictions that were incredibly hard to test. The mathematics was forbiddingly difficult, and it didn't seem to connect to the rest of physics in productive ways. This period, roughly 1920 to 1960, is sometimes called the low water mark of general relativity. And it's a fascinating stretch. Because even during this quiet period, seeds were being planted that would eventually transform our understanding of the universe. One of those seeds had been planted by Schwarzschild back in 1916 with that troubling singularity at the Schwarzschild radius. Another was planted when physicists and astronomers began to realize that general relativity had something extraordinary to say about the universe as a whole. Not just about stars and planets and light rays, but about the shape and fate of everything. The beginning, the end, the entire cosmic story. The universe itself, Einstein himself, had been among the first to apply his field equations to cosmology. In 1917, just 2 years after completing the theory. And he immediately ran into a problem. When he tried to model the universe as a whole, a universe filled uniformly with matter, the equations told him it couldn't be static. It had to be either expanding or contracting. And Einstein, like virtually everyone else at the time, believed the universe was static, eternal, unchanging on the largest scales. So he did something he would later call his greatest blunder. He added a term to his equations, a constant, which he called the cosmological constant, represented by the Greek letter lambda, specifically to allow for a static universe. The cosmological constant acted like a kind of repulsive force that could balance gravity on cosmic scales, holding the universe in a delicate equilibrium. But in 1922, a Russian mathematician and meteorologist named Alexander Friedmann took Einstein's original equations without the cosmological constant and showed that they naturally describe a universe that evolves over time, expanding, contracting, or oscillating depending on how much matter the universe contains. Friedmann's solutions were mathematically rigorous and physically reasonable, but they were largely ignored. Einstein initially thought Friedmann had made an error, then retracted his objection, but still didn't take the expanding universe seriously. Friedmann died of typhoid fever in 1925 at the age of 37, without ever knowing how important his work would become. Then independently, a Belgian priest and physicist named Georges Lemaitre arrived at similar conclusions in 1927. Lemaitre went further than Friedmann. He connected the mathematical solutions to actual astronomical observations, noting that galaxies appeared to be receding from us. And he proposed something profound, that the universe had begun from a single primordial point, which he poetically called the primeval atom. And then in 1929, Edwin Hubble at Mount Wilson Observatory provided the observational bombshell. Galaxies are indeed moving away from us, and the farther away they are, the faster they're receding. The universe is expanding, it's not static, it never was. Einstein abandoned the cosmological constant and reportedly told Lemaitre that introducing it had been his biggest mistake. Now, here's where this gets really interesting. Because that cosmological constant, the one Einstein regretted, the one he called a blunder, it came back, almost 70 years later. The return of the constant. In 1998, 2 independent teams of astronomers discovered something that shook the foundations of cosmology. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both trying to measure how fast the expansion of the universe was slowing down. Because that was the assumption, right? Gravity pulls everything together. The universe is expanding, sure. But all that matter, tugging on all the other matter, should be putting the brakes on, gradually decelerating the expansion. The question wasn't whether the expansion was slowing. It was how much. And the answer they got was, it isn't slowing down at all, it's speeding up. Let that sit for a moment. The expansion of the universe is accelerating. Something Some mysterious energy, woven into the fabric of space itself, is pushing everything apart faster and faster. And when they worked out the math, when they tried to describe this accelerating expansion within the framework of general relativity, they found that the equations needed exactly the kind of term Einstein had introduced back in 1917 and then thrown away. The cosmological constant, lambda. It was back, and this time it wasn't a fudge factor to keep the universe static. It was describing something real, a kind of energy inherent to empty space, pushing the cosmos apart with ever-increasing vigor. We now call it dark energy, and it accounts for roughly 68% of the total energy content of the universe. 68%. The ordinary matter you and I are made of, atoms, molecules, stars, planets, that's only about 5%. Dark matter, the mysterious stuff that holds galaxies together but doesn't interact with light, makes up another 27%. And the rest, the dominant component of everything that exists, is this dark energy, this cosmological constant that Einstein invented, regretted, and abandoned. Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics in 2011 for that discovery. And it's one of those beautiful, humbling moments in the history of science where the universe turns out to be stranger than anyone imagined, and where a theoretical idea that seemed like a mistake turns out to be more right than its creator ever knew. Einstein's intuition, even when he thought it was wrong, was operating at a level that still astonishes people. But here's the thing, we still don't really understand dark energy. We can describe it mathematically, we can measure its effects, we know it's there, but we don't know what it is fundamentally. Is it truly a cosmological constant, a fixed property of space-time itself? Or is it something dynamic, something that changes over time? There are models, quintessence, phantom energy, various modifications of general relativity. But none of them are confirmed. It's one of the biggest open questions in all of physics, and it flows directly from Einstein's field equations toward the singularities. Let's circle back to something we flagged earlier. Schwarzschild solution. Remember that troubling feature? A radius at which the math seemed to blow up? The Schwarzschild radius. For our Sun, that radius is about 3 kilometers. For the Earth, it's about 9 millimeters. The question that haunted physicists for decades was, is that singularity real, or is it just a quirk of the coordinates? For a long time, most physicists, Einstein included, believed that no real physical object could ever be compressed to its Schwarzschild radius. It seemed absurd. Nature, they figured, would find some way to prevent it. But starting in the late 1930s, that confidence began to crack. In 1939, J. Robert Oppenheimer, yes, the same Oppenheimer who would later lead the Manhattan Project, along with his student Hartland Snyder, published a remarkable paper. They showed that a sufficiently massive star, once it exhausts its nuclear fuel, could collapse under its own gravity with nothing to stop it. The collapse would continue past the Schwarzschild radius, and the star would essentially disappear from the observable universe, leaving behind a region of space-time so warped that nothing, not even light, could escape. Think about what that means. Space-time can curve so severely that it closes off a region entirely. Light, which always travels along the geometry of space-time, remember that's what general relativity tells us, light follows the curvature. Light aimed outward from inside this region would find that every possible path curves back inward. There is no outward direction anymore. The geometry itself has become a trap. But even Oppenheimer's paper didn't settle the matter. The physics community was distracted by the war, by quantum mechanics, by the sense that general relativity was a beautiful but somewhat impractical theory. It wasn't until the 1960s that things really changed. And the person who changed them more than anyone else was a quiet, meticulous English mathematician named Roger Penrose. In 1965, Penrose published a paper that was only a few pages long. But it contained an idea of extraordinary power. He introduced what are now called trapped surfaces. A topological concept that showed under very general conditions that once gravitational collapse passes a certain point, the formation of a singularity is inevitable, not just possible. Inevitable. The beauty of Penrose's argument was that it didn't depend on perfect symmetry. Schwarzschild's solution assumed a perfectly spherical collapse. You might think that any tiny asymmetry, a bump here, a wobble there, would prevent the singularity from forming. Penrose showed that it doesn't matter. The singularity forms regardless. This was a genuine breakthrough, and it earned Penrose the Nobel Prize in Physics in 2020, 55 years after the paper was published, which gives you some sense of how long it takes for the deepest ideas to be fully appreciated. The term black hole, by the way, didn't come into common use until 1967, when the American physicist John Wheeler popularized it. Before that, people called them frozen stars or collapsed stars or various other names. Wheeler had a gift for vivid language. He's also the one who coined the phrase "it from bit," suggesting that information might be more fundamental than matter. But black hole is the name that stuck. And it's a good one because it captures the essential idea, a region of space from which nothing returns. The observational revolution, and then came the observational evidence. Throughout the 1960s and 1970s, X-ray astronomy revealed objects in binary star systems that were incredibly compact and incredibly massive. Too massive to be neutron stars, too compact to be anything else. Cygnus X1, discovered in 1964, became the first widely accepted black hole candidate. Stephen Hawking famously bet against it being a black hole, then he conceded the bet in 1990. And then in 2015, exactly a century after Einstein completed general relativity, the LIGO Observatory detected gravitational waves for the first time. The signal came from two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging roughly 3 billion light-years away. The ripple in space-time that reached Earth was unimaginably faint. It stretched and compressed the 4-kilometer LIGO detector arms by less than 1,000th of the diameter of a proton, and yet they measured it. That's engineering and physics working together at a level that's almost hard to believe. The gravitational wave signal matched the predictions of general relativity with stunning precision. The waveform, the shape of the signal as it evolved over time, traced out exactly what Einstein's equation said two merging black holes would produce. A century-old theory tested in the most extreme conditions imaginable, and it passed perfectly. Kip Thorne, Rainer Weiss, and Barry Barish shared the 2017 Nobel Prize for the detection. And then in 2019, the Event Horizon Telescope collaboration released the first image of a black hole shadow, the supermassive black hole at the center of the galaxy M87, about 5 billion times the mass of our Sun. It looked almost exactly like the simulations predicted from general relativity. That glowing ring of superheated gas, the dark shadow in the center where light cannot escape. It was real, it was there. And it looked like what Einstein's maths said it should look like. The great unfinished business. So here we are, a theory that started with a young man imagining what it would be like to ride alongside a beam of light, has given us the tools to understand the birth and fate of the universe, the warping of time by gravity. The existence of objects so dense that space itself becomes a one-way door. And yet, and this is important, and this is something worth sitting with as you drift, general relativity, for all its breathtaking success, is not the final word. We know it's incomplete. We know this because there's another great theory of physics, one that governs the very small: quantum mechanics. And the two theories, as they currently stand, are fundamentally incompatible. General relativity describes gravity as smooth, continuous curvature of space-time. Quantum mechanics describes the other forces of nature: electromagnetism, the strong nuclear force, the weak nuclear force, as mediated by discrete particles governed by probability and uncertainty. Both theories are spectacularly well tested. Both are correct in their respective domains. But when you try to combine them, when you ask what happens at the center of a black hole, where all the mass is crushed to a single point, or what happened at the very first instant of the Big Bang when the entire observable universe was smaller than an atom, the math breaks down. You get infinities, nonsensical answers. The theories refuse to speak to each other. This is the great unfinished business of physics, the search for a theory of quantum gravity, something that reduces to general relativity at large scales and to quantum mechanics at small scales, but is deeper and more complete than either. String theory is one attempt. Loop quantum gravity is another. There are others still. None of them are confirmed. None of them have made a prediction that's been tested and verified. It's an open frontier. It's been open for the better part of a century. But what's remarkable, what's genuinely moving if you think about it, is how far we've come with the tools Einstein gave us. The field equations he finalized in November 1915, scrawled on a chalkboard in Berlin while the world was tearing itself apart in war. Those equations predicted the expansion of the universe before anyone observed it, predicted black holes before anyone believed in them, predicted gravitational waves before anyone could detect them, predicted gravitational lensing before anyone photographed it. Every major prediction has been confirmed. Every test has been passed, and the theory keeps revealing new layers of meaning as our instruments grow more powerful and our questions grow more precise. As you're lying there listening, as your breathing slows and your thoughts begin to settle, know that the same space-time that Einstein described is curving gently around you. The Earth's mass dimpling the fabric beneath you. Time ticking just a little bit differently for you than for someone in orbit overhead. It's all real. It's all happening. And in its own quiet way, it's quite wonderful.